Thank you, Frederico, for your introduction, and thank you all for coming to this talk this afternoon. We entitled this talk, as Frederico said, Smart Structural Composites Leveraging Piezoresistive Technology for Self-Sensing. This work is part of my career development project. The name of the project is Eco-Sense-Heal, Self-Sensing and Self-Healing Composites for High Responsibility Application based on recycled materials. This project is financed by the Portuguese Foundation for Science and Technology and is taking place here in this faculty at C-MAST. This is an individual project, but of course the results come from the contribution of several people, as I mentioned in the first slide. Introducing the topic, the main objective of this work and of this project is to produce and develop lightweight multifunctional structural composites with integrated self-sensing capabilities and in the future self-healing and recycling possibilities. The presentation of today is only related to the self-sensing abilities, but in the future we want to develop and to implement the self-healing and recycling possibilities in these materials. This is the main goal of the project. So produce lightweight multifunctional composites that can perform the role of structural components in a specific application, for instance, aerospace, aeronautics, and at the same time the material have the needed properties to function or to present different properties and different characteristics and be at the same time a self-sensing system, a self-healing material, recycled, so to develop multifunctional composites. The main function is structural, and the other ones give to the material this idea of multifunctionality. To understand a bit more and to introduce the importance of these topics of the advance of the composite materials, I bring here some data related to the markets of composites. In this case, advanced composites and fiber reinforced composites. Both markets are forecast to grow significantly in the next years in this decade, and the value of the market will grow for the next years. And this is important because we are researching new materials, new technologies in this area, and this area is the value of the field is increasing. So probably if we develop good solutions, the possibility of application and transfer of the technology to the market is bigger, because the money that is being invested in these markets is also big. These composite materials find application in different markets, in different types of industries. Aerospace, automotive, probably the most representative and the most recognized for everybody, but also in energy production, civil engineering and building, sports equipment, electronics, medical devices, and other possibilities. If we also analyze the numbers and the money involved in these markets, in more specific markets like the marine market, wind turbines market, advanced polymer composites market, and also the aerospace market, the perspective of growth in the next years is also interesting, and the value involved in these markets will increase in the next year. And as I said before, this is a good perspective for us that are working in this type of solutions, that the market is growing and the possibilities of investment probably will increase also. Specifically the aerospace market, here we have two well-known aircrafts from two also well-known companies that present in his composition a minimum of, in this case we cannot see, but is 50% and here 53% of composite materials. These numbers show the importance of this type of materials. The composite materials are being applied as half of the constitution of this aircraft. So the application of these materials is really important, as we can see here by these numbers. And why these composite materials are so interesting for this market and are so his application reach these levels. This is the main reason. The specific strength of this material is really high, and even higher than the conventional metal matrix solutions, steel or aluminum, titanium, nickel, and other metal matrix. The specific strength of polymer matrix composites is really high. And when we are talking about transport market, the weight of the structure is important, because less weight means less energy to move the structure, less energy consumption, less carbon CO2 emissions, and this is an important aspect of these materials and an important characteristic of these materials. This is why they are so applied. However, the application of these materials has some limitations, and they present also some disadvantages. One of the main ones is their low resistance to impact. When an object impacts the structures, typically we have this type of damage propagation. In the surface that is impacted by the object, we can see, or sometimes it's not so visible, a small indentation in the structure, in the place where the object impacts the structure. But there is a propagation of the damage through all the structure that is not visible in the upper side of the sample that is hit. And in the opposite side of the surface that was hit by the object, typically catastrophic damage occurs. Fiber breakage, delamination, and this type of damage will really compromise the structure in its function. This is the typical damage that occurs during an impact occurrence, and this is a fragility of this type of materials. Other issues and other limitations of the materials are related to the high carbon footprint that the synthetic polymers exhibit during all the life cycle of the materials, from the beginning, the extraction, from the petrochemical extraction, then during the utilization, and in the end of life. Typically these materials create big amounts of pollution in the water resource, in the lands, in the air, and this is also a big concern and a big limitation of the massive use of these materials. So this, mainly these two limitations that I present are in the base of our motivation to develop this project. Our idea is to introduce the ability of self-sensing in these materials, and the structural material itself can perform what we call the structural health monitoring without the attachment of external sensors that can compromise the structure, the surface, and interfere in the aerodynamical performance of the material. So what we want is to endow the structures with the capability of become a sensor itself, the structure. This is called also, normally is usually called self-sensing, is the ability of the material sense its own condition. The material itself is used as a sensor. So we don't need the attachment of extra sensors that can compromise the structure or affect the aerodynamical performance of the material. In our case, we are studying the piezoresistive self-sensing. The piezoresistivity is a property exhibited by some materials that consists in the change of the electrical resistivity of the material when an applied stress when a mechanical information is applied to the structure. Typically, we have here in these two graphs a representation. We have the curve of the variation of an applied stress, and the electrical resistivity also varies according to the applied stress to the structure. We will see this in more detail in the next slides. To achieve this piezoresistivity effect in these materials, we need to change them, because typically a polymer matrix, which is the base of these materials, is an insulated material. And in this type of materials, the piezoresistive effect is not so visible or exacerbated in an amount that could be used for self-sensing piezoresistive systems. So what we are doing is to dope and to have carbon nanotubes, which are electrical conductive particles, into the polymer matrix to make the structure semiconductor in the electrical resistance range. So initially, the polymer matrix is an insulating material. After, when we have some amounts of carbon nanotubes, the structure becomes semiconductive. And in this range, the piezoresistive effect is really, we can really observe this effect in the structure, and we can use it to promote and to develop the sensing solutions we are studying. The amount of carbon nanotubes that we need to have to the structures in our study are below 1% in weight. So we are talking about the very low percentage of this material. So moving into the experimental results, I will present the study of two case studies that we implemented in the laboratorial experiments. We studied this system or this solution in laminated composites that are typical composite materials that are used, for instance, in aircrafts and airplanes, and also in single lap joints, which is a solution very common also in aerospace structures, in cases that the bond of some components should avoid screws or should avoid the presence of holes that can compromise the structure. So we applied this concept of self-sensing, piezoresistive self-sensing, in these two case studies. To the manufacturing of the samples to perform the study, we used glass fiber as the fiber reinforcement, carbon nanotubes as a nano-reinforced, and the polymer matrix was a conventional epoxy resin. For the first case study, the laminated composites, we produce layered glass fiber composites, both two sets of samples. The first one, 12-layer composites of glass fiber epoxy, so pure epoxy with glass fiber reinforcement. This is the control sample. And the samples in which we studied the piezoresistive effect, we had the epoxy resin with 0.5% by weight of carbon nanotubes. For the second case study, we produced first the adhesive we used to bond the adherents. Bulk adhesive, we studied the bulk adhesive with 0.5 of carbon nanotubes, and then we use this adhesive to produce bonded single lap joints with epoxy resin heavy with 0.5 carbon nanotubes, and we use adherents of glass fiber also. In the first case study, we perform mechanical characterization of the samples, the typical and the standard 3-point bending tests. We did cyclical tests and also monotonic tests till the rupture of the samples. And we also studied, we performed studies of low velocity impact to understand how our structures behave in this kind of impact occurrence. As I said, is a real concern in the application of these structures. During the tests, we monitor the electrical resistance with a digital multimeter. Moving to the results, the first thing we did was to study the influence of the carbon nanotubes in the mechanical properties of our materials. As we introduced, as I said, 0.5% of carbon nanotubes in the laminate composites, it was important to understand how the presence of the carbon nanotubes will affect the mechanical properties of the materials. And we verified that in the samples before being impacted, before the impact tests, samples with carbon nanotubes present higher mechanical strength and higher flexible models, so the addition of the carbon nanotubes improve the mechanical properties. So here we will achieve a double effect, a double positive effect. By one side we can reinforce the mechanical properties, and in the other side, with the addition of the carbon nanotubes, we will impart the piezoresistive properties to the structure. Then we studied the same in the impact tests, low velocity impact tests. We perform impact tests of 3 Joule and 6 Joule, and in both cases we see that the carbon nanotubes improve the energy absorption capacity of the composite. So once again, the introduction of the carbon nanotubes improve the mechanical properties of our composites. These two microscopic images are interesting to show what I mentioned before in the beginning of the presentation. Here we can see what happens in the composite structure in an occurrence impact event. Here in this zone impacted by the object, we can see the presence of an indentation, but the damage that occurred inside is not visible here. And here, in this case of the 6 impact joules, we see, of course, the indentation, but in the hydrogen side, in the opposite side of the composite, we can see that big damage occurred. We can see fiber breakage, lamination, shear cracks. So this kind of impact really compromises the structure. This is why it's so important try to monitor this kind of events by this piezoresistive means, as I will show you in the next slides. We also studied the influence of the carbon nanotubes in the samples after the impact. And here we can verify that the samples headed by carbon nanotubes, the composite samples, present a less reduction in the mechanical properties after the impact. Once again, the carbon nanotubes improve the mechanical properties. Okay, now let's move to the electromechanical properties, which are I would say the most or the main results that I want to show you here. We start by studying the piezoresistivity of these laminated composites under flexural experiments by 3-part bending tests. And here in this graph, we have the black line that corresponds to the mechanical signal, the mechanical deformation, and the red line is the electrical resistance variation. And we see an overlap of both signals during the 5 cycles of the experiment. It means that there is a real-time synchronism between the mechanical signal and the electrical signal, and this is exactly what we want to achieve, a good relation between the mechanical deformation and the electrical variation that can give us an idea about the deformation that is being imposed to the structure. This good relation was observed in cyclical tests, but also in monotonic tests till the rupture of the sample. We can see that when we apply stress, the electrical resistance of the material increases, and when we are reaching the limit, the maximum stress that the structure support, the sample support, we can see the appearance of some noise in the electrical signal, which means that some defect are being, some permanent defect are being imposed to the sample, and this is exactly what we want to achieve. A good correlation between the mechanical part and the electrical part, and if we control the electrical, if we measure the electrical signal variations in real time, we can conclude, we can have an idea about the integrity of the sample. These experiments are for samples before the impact tests. Then we study the same properties in the samples that were impacted, in this case 3 impact joules, and here we see the same behavior but with some difference that indicate the permanent damage of the samples. We can see here some deviations of the electrical signal in red line against the black one that corresponds again to the mechanical signal. We can see here that we have some deviations during the experiment. This means that the sample that has been subjected to impact tests before present some damage, and the correlation between the mechanical and the electrical signal is not the same as we have at the beginning. So this is working as a sensor, this answer. In the monotonic test, until the rupture, we can see the same. The noise in the end of the experiment is even bigger than it was in the case of the original sample before the impact tests. We study the same after 6 joule impact tests. In this impact tests, we saw in the microscopic image severe damage was imposed to the samples, and here the deviation is even higher. Here we are in the cyclical tests, below or inside the elastic region of the sample, but we can see deviations of the electrical signal from the mechanical one during the cyclical tests, which means that severe damage was imposed to the samples. And here in the monotonic test is even more evident. A lot of noise during all the experiments is a signal of mechanical damage. We went even further and we control the signal, the electrical signal, during the impact tests for both 3 joule and 6 joule impact tests. And here in this graph we have the electrical resistance variation as a function of the time during the impact tests. At the beginning, the resistance of the materials was very low compared to the values that were reached after the impact. So here we can see that immediately after the impact we have a significant increase in the electrical resistance of the materials. So the system was able to detect the impact occurrence. But even more, with estimating the variation of the electrical resistance, we can have an idea about the energy that was involved in the impact. So the samples were able to detect the presence of an impact, and also measuring the electrical resistance variation, we can have an idea about the energy that was involved in this impact. So I would say that these results show that we are in a good way to produce self-sensing composites that are able to detect the presence of damage in real-time application, or also in an inspection post after the operation of the structure. Now moving to the second case study, the study of the single lap joints. These results of this case study, I would say, are a bit preliminary compared to the previous ones, and we will understand why. Here we also perform 3-point bending, in cyclical mode and in monotonic mode to the rupture of the sample, and we also perform shear spring tests to the single lap joint to understand how it behaves during the failure of the bonded joint. During the test, also again, we monitor the electrical resistance. Here we have the piezoresistivity of the bulk adhesive. So this results regards to the bulk adhesive. We produce first the adhesive headed with carbon nanotubes, and we study first the adhesive. And here we can see that the adhesive answers, it presents a piezoresistivity that was sensible to the variation of the strain. We increased the level of strain and we measured the electrical resistance variation, and we observed that there is a correspondence between these two signals. But here the electrical signal is not so clean like it was in the first study. In any case, I would say that this signal is the signal measured directly by the multimeter. This signal was not filtered, was not optimized, so we know that we have space for some improvements here. But the most important conclusion of this test is that this adhesive, composed by epoxy resin added with carbon nanotubes, is really sensitive to the electrical resistance variations when mechanical stress is applied to the builds. Then we applied this adhesive to glue adherents to build the single lap joint, and we test again the piezoresistivity of the structure in cyclical 3-point bending tests in flexible mode, of course. And here we verify again that when the sample is the stress is applied and removed, the electrical resistance varies again. But here the variation is the opposite of the first case. Here we have a negative piezoresistivity. What this means? In the first case, when we applied stress, the electrical resistance increased. Here, when we applied stress, the electrical resistance decreased. This is not important for the sensor building because the most important characteristic of this system is the presence of a variation of the electrical resistance when the mechanical stress is applied. The way that it varies, this is defined by the movements of the electrical charge carriers inside the polymer matrix during the experiment. But this is not so important. What is really important is this variation, this amplitude of signal during the test. We also perform long-term tests, also flexural tests, to see the stabilization of the signal over time. Here we perform 106 cycles, and we observe that after 25-30 cycles, the signal tends to stabilize in a plateau value and with a regular amplitude, which is also important to make some conclusions about these variations. After we perform the single, the shear test in a single lap joint, so we till the rupture of the joint. And here in this image, we can see and analyze what happens to the joint during the test. And once again, the black line is the mechanical data, and the red line is the electrical resistance. And here we can establish some correspondence between the different moments that happen during the test. In this image number 2, we can see the beginning of the fracture of the joint. And this moment 2 corresponds to the first increase of the electrical resistance in the measured value. And here, the moment 3, again, we have the beginning of the fracture in the opposite side of the joint. It also corresponds to the beginning to a marked increase of the electrical resistance. And the final break of the joint corresponds to the infinite increase of the electrical resistance. So once again, the real-time monitoring of the structure, in this case, this is a single lap joint with the control of the electrical resistance, can give us an idea about the integrity of the joint. To conclude, some final remarks and conclusions. First, in the first case study, the laminated composites, we observed that there was a good relationship between the relative electrical resistance variation and the mechanical strength in the bending bond. And we also observed that we can detect the occurrence of an impact element, and at the same time we can have an idea and estimate the energy that was involved in this impact. In the second case study of the single lap joints, We also observe a good piezoresistive trend that vary according to the different strain rates that were applied in the bulk exit in bending mode. We also see a stabilization of the signal over time for the single lap joint, and in the real-time damage monitoring, we can detect the different moments and the different cracks that happen in the joint during the shear strain tests. So, general conclusions about the work and the project. First, the addition of the carbon nanotubes imparts piezoresistive properties to the composites, which was the main objective of this additivation. Second is what I call the double positive effect of this additivation. The carbon nanotubes in this percentage of 0.5 Wh% also improves the mechanical properties of the composite, so is an additional good result of this manufacturing process. And as a final conclusion, for now, we would say that these composites are really promising candidates to produce structural health monitoring self-sensing systems based on these materials. The impact that we expect with this technology. So first, with this technology, we feel that it's possible to detect damage early. So in an early stage, and avoid that the propagation of the damage will compromise the structure. We can also propose continuous and real-time monitoring of the structures, and with this probably reduce the maintenance costs of in the structures which these materials are applied. As a consequence, we increase the safety of the system. We can also extend the life of the structures, and if we extend the life of the structures, we will reduce the consumption of raw materials, because we will need new raw materials later with these systems implemented. So, as a final consequence, we will reduce the consumption of energy, in this case fuel, and reduce the carbon CO2 emissions. To finish, I would like to thank to the Portuguese Foundation for Science and Technology for the financing to my individual contract here in C-MAST, in the Faculty of Engineering, and of course also thanks to the team, also to all the people that is involved in this project. Some of them are here: Lilio, João, Vera, Duarte. I thank you also, Francisco also, sorry. I also thank you for all the support and help to make this project happen. And thank you all for your attention.